Have you ever stopped to think about how a simple spark of electricity somehow powers the incredibly complex logic inside your phone? Well, in this explainer, we're going to take a high-speed journey from the most basic laws of circuits all the way to the design of the electronic systems that literally shape our world.
So here's our game plan. We'll start with the absolute bedrock, the DC foundation. Then we'll ride the wave into the world of alternating current. After that, we'll take a peek at the advanced tools engineers use, witness the semiconductor revolution that changed everything, and finally see how it all comes together to design the future. To really get a grip on how any of this works, we have to start at square one. We need to learn the basic language of electricity. You know, the fundamental concepts that describe every single circuit.
First up is voltage. Honestly, the easiest way to think about it is as electrical pressure. Just like water pressure in a hose, voltage is the force, that oomph, that's pushing electric charge and getting it to move. No pressure, no flow. It's that simple.
Okay, so if voltage is the pressure, then current is the actual flow. It's the measurement of how much charge is actually moving past a certain point in a certain amount of time. It's the water itself flowing through the hose.
And rounding out our big three, we have resistance. See, every material puts up a little bit of a fight against that current. You can think of it like pinching the hose. It makes it harder for the water to get through. That opposition to the flow, that's resistance.
So you've got these three core ideas. And what's so amazing is that they're all connected by one beautifully simple and powerful rule: Ohm's law. It just says that voltage equals current times resistance. With that single piece of grammar, you can understand the behavior of almost any basic DC circuit.
And this quote just nails it. Voltage, current, and resistance, they aren't really separate things. They're all just different ways of describing the behavior of one fundamental property of our universe, and that's electric charge.
Now, for more complex circuits, we need a bigger toolkit, and that's where Kirchhoff's laws come in. The current law, KCL, is pretty intuitive. It just says that whatever current flows into a junction has to flow out. Charge can't just vanish. Then there's the voltage law, KVL, which says if you take a trip all the way around a closed loop, all the voltage gains and drops have to add up to zero. It's all about conservation of energy. But what if a circuit is just a huge, tangled mess? That's where the pure genius of Thevenin and Norton comes in. These theorems give us a way to take any messy, complicated part of a circuit and replace it with a stunningly simple equivalent. It's the ultimate cheat code for simplification.
All right, we've nailed down the steady, one-way street of DC. Now let's switch gears and explore the dynamic, constantly changing world of alternating current, or AC. Yep, the power that comes out of your wall sockets.
So unlike DC's flat line, AC voltage and current are always oscillating in a smooth sine wave. This brings in a couple of new ideas. We get frequency, which is just how many times the wave repeats per second. And we get the RMS value, which is a really clever way to talk about the effective power of an AC signal, comparing it to its DC equivalent.
In the AC world, power isn't just one thing. There's real power, the stuff that actually does the work, like heating a stove, but there's also reactive power, which is energy that's just borrowed and returned by components to build electric and magnetic fields. Apparent power is the combination of the two. It's the total that the power grid has to be able to supply.
So that ratio between the real work you're getting done and the total power you're drawing, that's called the power factor. And it's basically an efficiency score. A perfect score of 1 means every bit of power is doing useful work. A low score means a lot of power is just sloshing back and forth doing nothing useful, which is super inefficient.
Now, when you have AC circuits with all three of our friends, resistors, inductors, and capacitors, something really magical can happen. It's called resonance. It's a very specific frequency where the energy-storing effects of the inductor and the capacitor are perfectly equal and opposite.
At this one magic frequency, the effects of the inductor and capacitor completely cancel each other out. They essentially become invisible, and the circuit acts like there's only a simple resistor there. This is the fundamental idea that lets you tune a radio to a specific station.
Okay, we've got the concepts. Now let's pull back the curtain and peek inside the engineer's toolkit at the seriously powerful math they use to predict exactly how these circuits are going to behave. Now, I know this looks intimidating, but the Laplace transform is basically a mathematical decoder ring. It takes really complicated equations that describe circuits over time and, poof, it transforms them into a much simpler world where the problems become basic algebra. You solve it there, transform it back, and you've got your answer. It's a lifesaver.
And if Laplace is the decoder, then the Bode plot is the treasure map. It's a standard chart that shows you, at a glance, exactly how a circuit behaves at every single frequency. You can see what it amplifies, what it blocks, and how it shifts signals. It's the visual signature for any filter or amplifier. So far, everything we've talked about has been a passive component. Now, we're going to pivot to the active components that started a revolution and power our entire digital world: semiconductors.
At the very heart of this revolution is the transistor. And there are two main families, the BJT and the MOSFET. Here's the key difference. A BJT is controlled by current, but a MOSFET is controlled by voltage. And that difference, plus the fact that MOSFETs are so efficient and can be made unbelievably tiny, is why they completely took over the world of digital electronics.
For all their complexity, transistors really only do two basic things. They can act as a lightning-fast switch, turning signals on and off millions of times a second, or they can act as an amplifier, taking a tiny little signal and making it huge. That's it. Every computer, every phone, every server, it's all just built from billions of these simple switches and amplifiers.
We've come a long way, from Ohm's law all the way to the transistor. So how do engineers actually take all these principles and use them to build the technology of tomorrow?
Well, today's design process operates on an incredible scale. Instead of circuits with a few components, engineers design integrated circuits, ICs, with billions of transistors on a single chip. This is only possible because of powerful simulation software that lets them build and test these entire massive systems in a virtual world, long before anything physical gets made.
So we've taken a journey from a single, simple law of electricity, all the way to simulating these vast, complex systems on a computer. Every single piece of modern tech is built on these foundational ideas. So with all that in mind, the only question left is, what will you design next?